This figure shows groundwater in a homogeneous aquifer captured between two impermeable layers, one at the bottom and one at the top. The water level in both canals lies above the bottom of the upper impermeable layer, causing the aquifer to be confined. The canals are incised to the top of the lower impermeable layer. For this, the expression fully penetrating canals is used. Because the water level in the left canal is higher than in the right canal, groundwater flows from left to right through the aquifer. The water in the canals is artificially kept at the levels indicated in this figure, this level and that level. Because of this, groundwater flow is steady, or in other words, stationary. The top of the lower impermeable layer serves as the reference level. At x is 0 meters, the hydraulic head in the aquifer, H0, equals the water level in the left canal. At x is L, the hydraulic head in the aquifer, HL, equals the water level in the right canal. In each point of the vertical in x is 0, the hydraulic head, or potential, has the same value H0. If we were to install a piezometer with its screen here, then this would be the elevation head and this would be the pressure head. If we were to install a piezometer with its screen here, this would be the elevation head and this would be the pressure head. Elevation head plus pressure head is hydraulic head, so everywhere along this vertical we have the same hydraulic head, and thus the vertical in x is 0 is an equipotential. The same reasoning goes for the vertical in x is L. Each point of the vertical has the same hydraulic head HL, and the vertical in x is L is also an equipotential, albeit with a lower hydraulic head value than at x is 0. Because the steady flow is from left to right and is confined between two impermeable layers, flow must be horizontal and at a right angle to both equipotentials in x is 0 and x is L. In other words, all verticals between x is 0 and x is L are equipotentials, with their hydraulic heads diminishing from left to right. Darcy's law for this flow case can be written as the volume flux Q equals minus K times A times HL minus H0 divided by L. HL minus H0 is the difference in hydraulic head. L is the distance over which this difference in hydraulic head occurs. So HL minus H0 divided by L is the hydraulic gradient. A is the area perpendicular to your water flow, and K is the hydraulic conductivity. This can also be written in the following shape: for an increment delta x along a streamline and a corresponding difference in hydraulic head delta h, Q, the volume flux, equals minus K times A times the hydraulic gradient, written as delta H delta X. If we take delta X infinitely small, we can write dH dx instead of delta H delta X for the hydraulic gradient. As A is the saturated area perpendicular to the groundwater flow inside this confined aquifer, this area A equals the vertical depth of the aquifer times the width W, which is the horizontal direction perpendicular to this cross-section. So going into the screen, and we can write that Q equals minus K times D times W times the hydraulic gradient dH dx. We can divide the volume flux Q by this horizontal direction perpendicular to this cross-section W, and then obtain Q with a prime equals minus KD times dH dx. Q with a prime is the volume flux or discharge per unit width of the aquifer. Per unit width actually means that we dispose of the width of the aquifer so that we only deal with the horizontal X and vertical Z dimensions of the cross-section. The volume flux per unit width, Q with a prime, has units of square meters per day, much the same units as the ones that you use when you paint your garden fence. In hydrological practice, groundwater flow problems are usually reduced to 2 dimensions in cross-section or plan view, simply for ease of calculation. Because the aquifer is homogeneous, the hydraulic conductivity K has the same value for every horizontal position X. The saturated thickness or depth D is also constant for every horizontal position X. Because the water in both canals is artificially kept at the levels indicated in this figure, and the volume of water entering the aquifer per unit of time to the left must equal the volume of water leaving the aquifer per unit of time to the right, there is, so to speak, no creation or destruction of water flow per unit of time within the aquifer. The hydraulic gradient must be the same for every horizontal position X. Thus, the hydraulic head linearly decreases with horizontal direction X. Mathematically, this linear relation between H and X can be written as follows. H equals C1x plus C2. Please note that in this figure, H0 has been taken as 10 meters, L as 100 meters, and HL as 8 meters. This picture also nicely shows how you can measure the hydraulic head in the confined aquifer by placing a piezometer tube with its screen within the confined aquifer. We could also have derived this linear equation for the hydraulic head H with horizontal position X, H equals C1x plus C2, as shown in the Mathematics Toolbox M1 at the end of my book. We will combine Darcy's law with the continuity equation. And this is standard procedure in hydrology. We will also be doing this, combining these equations for other flow cases. So here we have Darcy's law, here we have the continuity equation. When we combine these two for this flow case, this is the equation we get. Minus Kd times your hydraulic gradient is constant. Of course, K and D are constants, so we simply get dH dx is constant. We write that constant as C1. When we integrate this equation, this is what we get. What follows now is also standard procedure. We want to find out the values for C1 and C2. And you can find these values by inserting the boundary conditions. You always start off with inserting your left boundary condition, followed by inserting your right boundary condition. Let's start off with the left boundary condition. When x equals 0, then h equals h0. insert this into the equation and we get H0 equals C1 times 0 plus C2. So H0 equals C2. C2 equals H0. Let's now insert the right boundary condition. When x equals L, then H equals HL. From this it follows that HL equals C1 times L plus C2. And of course we already know that C2 equals H0. So HL equals C1L plus H0. So now we have found C1 as equaling HL minus H0 divided by L. Now insert these values for C1 and C2 in the original equation H equals C1x plus C2. Inserting the values found for C1 and C2 in that equation gives this final equation H equals HL minus H0 divided by L. Multiply this by x and then plus H0. HL minus H0 divided by L is the slope of your hydraulic head distribution, your potentiometric surface or your piezometric surface, and HL minus H0 divided by L is of course your hydraulic gradient. Also, this equation, derived from combining Darcy's law, the flow equation, with the continuity equation for steady groundwater flow, is called a Laplacian, after the French astronomer and mathematician Pierre-Simon Marquis de Laplace. When H0 is taken as 10 meters, L as 100 meters, and HL as 8 meters, this equation could also have been written as stated here.